Hello, welcome to part 2 of our lesson on influence line, which is a method of analyzing structures in civil and structural engineering. My name is Engineer Dr. Edidiong Ambrose from the Department of Civil Engineering at Akwa Ibom State University. So in the first part of our lesson, the first part of this lesson, we did introduce the concept of civil engineering. We did analyze how to draw the influence line for support reactions, for shear force, and for bending moment. And we did solve two examples on how to analyze the influence line when a concentrated load is moving across a span of a beam and when a uniformly distributed load is moving across the span of a beam. And in this part of the lesson, we are going to solve two other examples to reinforce our understanding of the concept of influence line. So we go to example 3. Example 3 say there is a figure here. It says for the beam in figure Q3, draw the influence line diagram for one reaction at A, then reaction at C, shear force at B, bending moment at B. So this is the beam. Each has point. This is support at A, support at C, and this is point B, which is a midspan between support A and support B. The beam is actually cantilevered by 3 meters by right hand side. So the big question say use the influence line diagram in section A to calculate the maximum values of each of the actions in 1 to 4 when a concentrated load of 35 kilonewton moves from left to right across the beam. And the C part say use the influence line diagrams in section A to calculate the maximum values of each of the actions in 1 to 4 when a uniformly distributed load of magnitudes 15 kilonewton per meter and length 3 meter moves from left to right across the beam. So quickly we are going to start. The A part was that we should draw the influence line diagram for reaction at A, reaction at C, shear force at B, and shear bending moment at B. So we start by drawing for reaction at A. So let's calculate the reaction at A. The reaction at A. So as usual, this is the beam. We introduce a unit load that is a load of 1 kilonewton, taking support A as a reference point. This load is moving, that's why we keep X, because this X can change. So we now say when X equals to 0, that is when X is equal to 0, this 1 kilonewton load will be directly on top of VA. And because of that, the value of VA will be 1 because VA will be carrying the load complete on its own. So the value of VA will be 1 kilonewton. I think if you want to confirm, you can just use the concept of force resolution and then analyze the load by placing the 1 kilonewton load here, analyzing the value of VA. In that case, the best thing to do will be to stand at C and take moment. And take the moment at point C and then equate it to 0. You'll be able to calculate VA and find out that VA will be 1 kilonewton. So in the same vein, when X equals to 7, when X is equal to 7, this is from A, this is 0.7, C is 0.7. So that means the point load, the 1 kilonewton load will be directly on top of C, on top of VC. And so in that case, VC will be the one carrying out the load. And so VA will be equals to 0. And so, like say when X equals to 7, VA will be equals to 0. Now, when X equals to 10, the 1 kilonewton load will be direct at D. And if you do force resolution by taking moment at point C, then VA, the value of VA will be minus 3 over 7. So with this information, we can plot the influence line for reaction at support A, which is if we come here, when x equals to 0, VA is 1, so at this point VA is 1. When x equals to 7, VA is 0, so at this point VA is 0. When x equals to 10, VA is minus 3 over 7. Minus 3 is downward. That's why we have minus 3 over 7. So if we plot it, this is what we will have. So this is the influence line for reaction at A. So in the same way, we can go for reaction at C. So with this, our diagram, as usual, when x equals to 0, that is when the 1 kilonewton load is directly on top of VA. VC will be 0. So VC will be 0. When x equals to 7, when the load is 1 kilonewton load is directly at C, you can say when the load is carried, the load will be carried only by VC. So VC will be equal to 1. Like I said, all those things you can do it by using the concept of the principles of equilibrium, that is taking moment. Like if you want to find VC, you can place the load here, take moment at point A, you will have the value of VC. So when x equals to 10, that means when the 1 kilonewton load is here at the cantilever end at point D, if you do force resolution, VC is equal to 10 over 7. So with this information, we can also plot the influence line for reaction at C. That is influence line for VC. Remember when x is 0, VC was 0. That is why this place is 0. When x is equal to 7, VC was 1. That is why this place is 1. When x equal to 10, VC was 10 over 7. That's why we have 10 over 7 here. So if you join, that gives you a plot of the influence line for reaction at C. So let's proceed. Let's also do for shear force at B. This is point B. Point B is midway between support A and support C. So we have point B. So as usual, for us to draw the influence line for shear force at B, we will place at 1 kilonewton. Remember, this load is 1 kilonewton, so you can put it. We'll place at 1 kilonewton load here. When we place a 1 kilonewton load at the varying distance of x. So when x equals to 0, that is when the 1 kilonewton load is directly on top of V. This is VA. When the 1 kilonewton load is directly on top of VA, what will be our VA? VA will be 1. If you remember, if you doubt it, you can do equilibrium of forces. So VA will be 1. So when VA is 1, what is shear force at B? Remember, I like to define shear force. Shear force is the algebraic sum of all the forces either to the left or to the right of a structure. So let's do everything to the left here. So we can say that our shear force is the algebraic sum of all the forces to the left of point B. So if the 1 kilonewton load is here, you have two forces to the left of point B. This is B, this is the left of B. So the first one is the reaction at A, VA, which is going up, and we say VA is what? This is VA minus the 1 kilonewton load that will be on top of VA, and the 1 kilonewton load is coming downward. So that's why it is minus. So we now have VA minus 1, and VA is 1. So 1 minus 1 is 0. So that gives us the shear force at point 0. So if you come here for the shear force diagram, this point is 0. The next thing is to calculate the shear force at the point that we are considering. And at that point, remember, we always have two shear force. One is inside A, just immediately B, and one is just immediately after B. Okay, so we now at that distance B is 3.5 from support A. So we now say when x is equal to 3.5, if we analyze VA when the 1 kilonewton load is at VB, if you analyze that, VA will be 0.5. So that means shear force at B will be, when you are the 1 kilonewton load is just before B, that means it will be in the left of B. In that case, the left of B will have two forces, the support reaction VA and the 1 kilonewton force. And so if that is the case, we now say when x equal to 3.5 and VA is 0.5, that shear force will now be VA, which is going upward, minus the 1 kilonewton load, which is coming downward. And we know VA is 0.5, so 0.5 minus 1 will be minus 0.5 kilonewton. And so we do when the force have just passed B. What the implication is that when the force have just passed B, it is no longer in the left of B. So when you are looking at all the forces in the left of B, you will only have this force support reaction, which is, in this case, we say when x equal to 3.5, VA is 0.5, VA is 0.5. So shear force will just be VA, which is 0.5. So you now have two forces at point B, two shear force. One, when the load is just before B and the shear force is minus 0.5, and when the load is just after B, the shear force is 0.5. So if you plot the two, look at it, that's why minus is in shear force diagram, minus is always down. So we have 0.5 here, this is minus 0.5. At that same point, we have plus 0.5, plus is up, minus is down for shear force. So that's why we move from 0 to minus 0.5, and then we move to plus 0.5. Now the next point to calculate shear force is point C, when x equals to 7. So we say when x equals to 7, remember at that point the reaction at AVA is 0. And so when you are there, when the 1 kilonewton load is here, is only VA that will find, which is going up and is positive. So we say shear force at point B will be VA, and VA is 0. So that's why at that point the shear force is 0. You can see it went to 0.5 and is coming down to 0.0. So we now go when x is equal to 10. That means when the 1 kilonewton load is here. Remember, when here the VA reaction at A was minus 3/7. And so when the load is here, we only have VA on the left. So the shear force at B when load is at D will now be VA and will be minus 3/7. So that's why the shear force move from 0 here to minus 3/7. Remember I said that shear force diagram, negative minus is downward, positive is up. So with this we have plot, this is the shape of the influence line for shear force at point B. Again, you are going to also plot the shear force diagram for bending moment at point B. This is point B, so we are going to plot bending moment. What is bending moment? Bending moment is the algebraic sum of the moment of all the forces either to the left or to the right of a section. But I always like doing to the left. That doesn't mean you cannot do to the right. So you have to calculate the moment of all the forces to the left of point B. So we go again. When x equals to 0, that means the 1 kilonewton load is directly on top of VA. What will be the bending moment? If you stand at point B, there will be two forces to the left of point B, which will be the reaction at A and the 1 kilonewton load, which will be directly on top of VA. And so we take moment. What is bend moment? Moment is force times perpendicular distance. So we now say when x is equal to 0, remember VA is equal to 1. So bending moment at B will be VA multiplied by the distance. So this is the VA. The perpendicular distance is 3.5. That is why we have VA into 3.5. And it's positive because VA is going up. The 1 kilonewton load will be coming down. And so it is minus. That is why we have minus 1, which is the 1 kilonewton load, and 3.5, which is the perpendicular distance between the load and where we are taking moment from. And because VA is also 1, so that will be 1 times 3.5 minus 1 times 3.5, and that will be 0. So go to the bend influence line diagram for bending moment. You see bending moment is 0 at that point. So next is when x equals to 3.5. Remember when x equal to 3.5, VA was 0.5 from our calculation. VA was 0.5. So when x is 3.5. That means this force of 1 kilonewton force will be directly on top of B. And when it is directly on top of B, this moment at point B will be 0 because perpendicular distance is 0. So we will only have one force by the left of B, which is the reaction. And so we now say at that point, V bending moment at B will be VA multiplied by the perpendicular distance, which is this is VA, this is the perpendicular distance, and VA is what? VA is 0.5. So we now do 0.5 multiplied by 3.5 gives us what? 7 over 4. That is why at that point B, the bending moment is 0, 7 over 4. Now for bending moment, we only have one value, not like shear force that we have two values just before and just after. For bending moment is just one value. So this place is 7 over 4. We now go to when x is equal to 7. That means when the 1 kilonewton load is directly on top of C. By that, you will only have one force by the left of B, which is the reaction at A. And the perpendicular distance between reaction at A and where we are taking moment is 3.5. So we say at that point, when x equals to 0, when x is equal to 7, VA will be 0, and because VA is 0, so 0 multiplied by the perpendicular distance is 0. So bending moment is 0. That's why the bending moment moved from 7 over 4 to 0 at point C. The next one is when x is equal to 10. That is when the 1 kilonewton load is directly on top of D, directly at point C. That is a cantilever point. Remember, VA at that point was minus 7 over 7, 3 over 7 kilonewton. And the bending moment, because bending moment at B, the only force by the left of B is VA. And the perpendicular distance is 3.5. So we now say VA multiplied by 3.5, which will be minus 3 over 7 multiplied by 3.5. That gives us minus 2 over 3. That's from another thing you notice for bending moment, positive is downward, negative is up. That is a sign convention. That is why when we have 7 over 4, it was down. And when we have minus 3 over 2, it is up. So the bending moment move from 0 to 3 over 2, minus 3 over 2. So you see the up portion is negative, the down portion is positive. And so with this, we have drawn the influence line for our reaction at A, which is this, reaction at C, which is this, shear force at B, which is this, and bending moment at B, which is this. So we now go to the second part of the question. We say that use the influence line diagram in section A to calculate the maximum values of each of the actions in A in 1 to 4 when a concentrated load of 35 kilonewton moves from left to right across the beam. What it means that a concentrated load of 35 kilonewton is moving across this beam from left to right. You should indicate at what point will the load be that we will have maximum shear reaction at A, and what will be the value. Do the same for reaction at C, shear force at B, bending moment at B. For us to know that, let's start with reaction at A. This is the influence line for reaction at A. So when we are doing a 1 kilonewton load is moving across, when a 35 kilonewton load is moving across. So all you do is look at the influence line. Where will you place a 35 kilonewton load such that when you multiply by the coordinate, it will give you maximum value? It will just common sense will tell you that if you place it at big points, either at this point A, at this point D, you will have. But this point, the coordinate here is 3 over 7, which is less than 1. This place it is 1. That means you will place the 35 kilonewton load here at this point. This way will give you maximum reaction at A. So if you place the 35 kilonewton load here, it will give you maximum reaction at A. So what do you do? And what is the coordinate at that point? The coordinate of reaction at A is what? Is 1. So that is why if you go to this solution, say from the influence line diagram in A, maximum action due to 35 kilonewton load will occur as follows. For reaction at A, it will be at when x equals to 0, which is what I've just showed you. And the magnitude at there is 1. So the maximum reaction at A will be 35 kilonewton load multiplied by 1, which will be 85. And so we go again. What about reaction at B? Where do we have the maximum coordinate here? The maximum coordinate in this place is 1, but this place is 10 over 7, which is more than 1. So that means it is when the load is at point B, point D, that we will have the maximum reaction at C. So you place the 1 kilonewton load, and what is the coordinate there? 10 over 7. So this is why we come here. You will notice they say VC is when x equals to 10, and VC will be 35 multiplied by 10.7, which gives us 50. And so we go to shear force. When we go to this is a shear force diagram. At what point will we place? Where do you have the maximum coordinate? This is 0.5. 3 over 7 is less than 0.5. So it is when you place the load here. And here we have the maximum coordinate that you will have the maximum shear force. But remember, this side above is positive, this side is negative. So it's either you place it on the positive side or you place it on the negative side. The concept of positive and negative is just to show the direction of shear force. So either we place it on top here, which the coordinate is 0.5, and the value will now be 35 multiplied by 0.5, or we place it here, which will now be 35 multiplied by minus 0.5. Both of them will give us the same answer. So that is why we come here. We say maximum shear force at B is 35 multiplied by 0.5, which gives us 17, or 35, sorry, this one was multiplied by minus 0.5, which gives us minus 17. This one is 35 multiplied by 0.5, which gives us 17. So either minus 17 or plus 17, they are maximum. The only two difference is the direction. This one shows that the minus 17 shows that the shear force is coming down. Plus 17 shows the shear force is going up. So we now go to the bending moment diagram. Where will we place the 35 kilonewton load in the bending moment diagram that will give us the maximum bending moment? So where do we have the maximum coordinate? 3 over 2 and 7 over 7 over 4. 7 over 4 is greater than 1. So we are going to place the moment here at when x equals to 3.5, that is at point B. So if we do that, what is the coordinate there? 7 over 4. So that is why we go there. Bending moment will be at when x equals to 3.5, and the maximum bending moment will be 35 multiplied by 7 over 4, which is the coordinate at that point, and that gives us 61.25 kilonewton. So the C part is that we had to determine the maximum. We're asked to find the maximum values. Okay, let's go back to the question. The question said, use the influence line diagram in section A to calculate the maximum values of each of the actions in 1 to 4 when a uniformly distributed load of magnitude 15 kilonewton per meter and length 3 meter moves from left to right across the beam. So a UDL of 15 kilonewton per meter and length 3 meter is moving across the beam from left to right. You are told at what position will the UDL be that you have maximum reaction at A? At what position will it be that you have maximum reaction at C? And then shear force and bending moment. So that is what we are going to do here. You see, this is the influence line diagram that we have derived for reaction at A. So where will you place? You go to, of course, you will place it from where you have the maximum coordinate. The maximum coordinate was 1 kilonewton, so we place it from here downward, and that gives us, remember, for us to find the reaction at A, we calculate the area of the shaded portions and multiply by the magnitude of the load. So this is where we do. So the coordinate here and from here to here is 3 meter. If you use similar triangle to find what is the coordinate at 3 meter, it gives us 4/7. So we have to calculate the area under this load and multiply by the magnitude of the load. So this is what we do. This shape, this is a trapezium. This is a trapezium. An area of a trapezium is half the sum of the two parallel sides multiplied by this distance. So we now say half. The two parallel sides are 1 kilonewton and 4/7. So that's why we do 1 plus 4/7 in bracket half of it multiplied by this distance. We call this distance, which is 3. We now multiply it by 3. That gives us the area of the trapezium. We now multiply the whole of that by the magnitude of the load, which is 15. And that gives us 35.36 kilonewtons. So that is the maximum reaction at A when the force is moving across the beam, the load. The same thing goes to VC. This is the influence line for VC. Where do we place the UDL? We place it at this side. We place it at this side, the highest point, and it goes this way. So the distance is 3 meters. That means it will occupy from that point D to where we have reaction at C. So 3 meters. Again, we calculate the area of the shaded portion. We multiply it by the magnitude of the UDL. So this is a trapezium again, and the two parallel side is 1 kilonewton and 10/7. So we do 1 plus 10/7. We multiply it by half, because the formula says half the sum of the two parallel side times the distance, this distance, which is 3 meters. We multiply by 3 meters, and we multiply everything by the magnitude of the UDL, 15 meters. And so the answer gives us 54.64 kilonewton. That means as the load is moving across the beam from A to B, the VC will be subjected to a higher reaction than VA. So we go and do the same for shear force. For this is a shear force diagram. This is a shear force diagram. This distance from, remember, from here to here is 3.5, here to here is 3.5, this is 0.5, this is 0.5. So for this shear force diagram, you could have placed it up, you could have also placed it. You could have placed it in this side, you could have also placed it in this side. It will give the same value, but that is not always the case. So this is a 15 kilonewton per meter load at the distance of 3. So if we place it here, look at the shaded area, 3 meters from here. The coordinate here, when calculated, gave us 0.07. Use the concept of similar triangle. And so the area, the shaded area, again, this is a trapezium. So the two parallel side is 0.5 and 0.07. So we now do 0.07 plus 0.5 in bracket multiply by half. When we multiply by half, then the distance, this distance is 3 meters. We multiply by the 3 meters, and we multiply everything by 15, which is the magnitude of the load. And everything gave us what? 12.83 kilonewtons. So that is the maximum shear force at B. The next thing we go is for bending moment. For bending moment, look at the way this is. We need to position the load such that we will have the maximum value. If we had positioned it here, from here to this side, it wouldn't have given us maximum value. So the maximum value was derived by placing the load such that half of it goes to this side, half of it goes to this other side. So that is what we did. That's why the load is placed such that 1.5 is this side, 1.5 is this other side. And we know that the mark point here is what? 7/4 from the influence line diagram we derive. And so we are going to have, if you divide this thing, this shaded area into 2, they are symmetrical. So you can calculate for one side and multiply by 2, which is what we do. We now say, okay, the two parallel side, if you are dividing it half here, the two parallel side will be 3.3/4 and then 7/4. So that's what we say. 3/4 plus 7/4. We now multiply by half. And we now multiply by the distance. The distance in that case will be from here to here, which is 1.5. And then we multiply the everything by the magnitude of the load. That gives us the bending moment for one side. To get for the other side, we multiply everything by 2. And it gives us 56.25 kilonewton meter. So with this, we have been able to solve example 3 completely. So let's continue. Okay, I've just discovered that this video is already 30 minutes, so we don't want it to be longer. We are going to stop it here. We are going to solve example 4 in part 3 of this lesson. Don't forget to subscribe to this channel if you have not done it. Thank you for staying to the end.